Okay, I'm going to talk about something that most people don't actually understand because unfortunately we don't really teach automata theory terribly well anymore. So everyone loves to run around and say Bitcoin's not Turing complete. Even PostScript is Turing complete, to tell you the truth. It's whether it's efficient or not, and we're actually going to start teaching you that Bitcoin is actually incredibly efficient as a Turing complete machine. Now, when you're developing coding, what you'll find is what you end up with is a number of functional blocks that are then looped. And each functional block is generally doing one thing without many loops. So Bitcoin follows what Turing did close to 100 years ago now with the idea of a simple alphabet that acts as a predicate. Each script in itself can be either unrolled, acting as a fully functional language, or further than that, it can be then looped into many things. The interesting thing that people don't get with a predicate-based system is only those predicates that end true end up being written into the blockchain. Now, that doesn't mean that you can't actually have multiple things. So if you look at CUDA programming, like you do with supercomputers, GPU programming, etc., what you end up doing is splitting out loops. You unroll because it's efficient, and the unrolled loops are then put out to many, many GPU or other processors, doing small components that the first one to end gives you the results. So that's generally how supercomputing works. It's massively parallel, and you run everything and then only want the result. So you could argue that supercomputers are incredibly wasteful because you run a whole lot of junk that never ends and the occasional script that does. That's similar to how Bitcoin is. So what we start with is we start with a typical sub-language and the accompanying properties. If you look at the paper, all this is defined, and we can actually do a complete proof with lambda calculus. Now, the reason for this is Bitcoin is a dual stack machine. So it's a 2 PDA. And anyone who has gone back and done enough automated theory will know that a 2 PDA enables you to copy back and forth in script. Now, the argument is with a block size limit that Core imposed, a 1 megabyte and a whole lot of other script limits and whatever else, that you can't do anything functional. But that wasn't how Bitcoin was actually designed. Not only can you, when you remove those limits, start doing about anything you could think of, you can then start actually building a different type of machine. So one of the things you can start doing is publishing functions. Each function is provably correct because you know that it does a certain task. The best ones can win because you can then have evolutionary coding and PSOs. The best functions over time get paid. Those functions that are paid keep running. Those functions that aren't paid starve. Effectively, if anyone's done PSOs, particle swarm optimization, or any other form of this coding, you'll then have a weighted function, but instead of an arbitrary weighted function, it comes down to economic certainty. If people want your code, people pay for your code. If someone develops a better function and places that as a script, then they start paying for that better script. So what we actually end up with is a number of conditions in our scripting language. I'm not going to talk so much through the lambda calculus of this. It's in the paper, but it enables you to effectively calculate anything. The problem many people don't understand is Turing complete just means it is calculable in unbounded time. Anything that a person, which a computer was back then, with a pen and paper and unbounded time can compute is Turing computable. It's just the ability to form that number. That doesn't mean that we want to necessarily do everything and put everything in a single script, but that's why you also think about parallelization. If you have hundreds of different scripts, all ending, all going to agents, all doing the equivalent of looping because you have payment channels on each of them, not a single payment channel. This is where people also never thought past where Bitcoin goes. If you then start thousands of payment channels, each payment channel can loop and settle immutably. Each one can interact with another. If you have multiple keys, you can start interacting between each of them. The way to think of this is massively parallelized systems. So the same as game developers make when they're doing online games that have to do a lot of processing very quickly. They flip it across to, on computers, on desktops now, sometimes 10,000 different cores. Each of those cores runs a different process, all of which give similar results and update parts. That's what we're wanting to do. So, things that we can do. We have different conditions in Turing completeness. We have things like write monotony. And each of these configurations can be set for each machine. The part of this to configure is not a single machine, but a multi-core machine. Each node effectively runs many, many different cores. Each of those cores would be a different transaction. As things like Bitcoin scale, they have more. Where we'll be taking Bitcoin in the next 10 years isn't what you've been hearing in the press. It isn't the 3 transactions per second. It is the 3 billion transactions per second, and then more. So, invertibility. Another simple thing, can we flip things? We have all of that. If you look at the scripting language within Bitcoin, it's based on Forth. And what people don't understand is how powerful Forth can be. When I started out my career, I was in the Royal Australian Air Force, and one of the things I got shunted off to doing because I could program was working on the F-111s and F-18s. The F-18s need a very fast system, basically for the heads-up display and everything like this in the 80s and 90s. The code was nowhere near what we had now. It's an incredibly underpowered machine that does things that are really remarkable, especially for the time. And that was actually programmed in Forth. So most people don't realize that, but multi-processing systems actually ran fighter jets. And the thing is, if a fighter jet lags, people die. So all of this was actually designed to be very fast. So we then have partial recursive functionality. Now, we can then demonstrate by saving values into the alt stack and using multiple stacks that we are able to not only copy data back and forth, but that we can now create any word that can be reordered, can occur multiple times, etc. Difficulty, of course, for many people is understanding that you don't want every node on the network running everything, not like the Ethereum model. That's not what decentralization means. Decentralization in Bitcoin was always about competition. People compete to do it quickly, and they get paid as miners to do it quickly. So we can do all our basic functions. We can set a zero function, a successor function, predecessor, universal selector. We can start the different schemas required for this, such as composition, recursion, etc. And over time, because of the dual stack functionality, even though the alt stack's probably more likely to be used something like a counter slash registry, enables us to actually create more and more complex script. So one of the things that we've been doing in the background that no one has known about is we're starting to develop compilers and a high-level language, which aren't out yet, but they will be, allowing you then to do things such as people did in old PIC databases. So all of this enables us to effectively have a new form of computation. So if we think to a Wang B machine back in the 50s and 60s and the concepts back then, Bitcoin takes us back to an earlier age of computing before Intel and Microsoft and people got lazy. Thank you.